If I handed you a beaker of water and told you to put your hand in, you'd probably hesitate and check the temperature first. No one wants this surprise ice bath. But temperature isn't the only thing that matters. You might also want to ask, what's the pH? Because, let's be real, sticking your hand into something acidic? Not a great idea. Of course, in the lab, I'm not putting my hand in water. I'm just putting molecules in water. But I like my molecules. And just like you'd check the water before putting your hand in, these same factors, temperature and pH, are crucial in my experiments too. This is Real Chem. When I run an experiment in water, I always monitor and control the temperature. That makes sense. Hot water and cold water provide two very different environments. The same is true for pH. If I prepare a solution, I don't want its acidity to fluctuate. I make sure that the pH stays at a specific value. Let's imagine a solution where the temperature and the pH are both fixed. Given that, what can we predict about how molecules behave in that solution? Temperature is all about the transfer of kinetic energy. pH, on the other hand, is about the transfer of protons. We know that adding kinetic energy makes molecules move around more. But what about protons? What do these protons actually do? For many molecules, the answer is nothing. They don't interact with protons at all. But some molecules, like weak acids and bases, have sites where a proton can either be present or absent. If the environment has lots of protons, these sites will be occupied with protons. If protons are sparse in the environment, these sites will not be occupied with a proton. One way to envision this is by applying Le Chatelier's principle to the dissociation of a weak acid. Putting a molecule in an acidic environment is like adding hydronium ions. The system will respond to counter that stress by shifting towards the conjugate acid form. Putting a molecule in a basic environment is like removing hydronium ions. The system responds by shifting toward the conjugate base form. But, and there's always a but, whether a molecule views the environment as acidic or basic depends on the molecule itself. To see why, we need to look at how the ratio of conjugate acid to conjugate base are related to the pH and pKa. Let's say we have a molecule with a pKa of 4. When the pH of the environment is equal to the pKa of the molecule, the concentrations of the conjugate acid and conjugate base are equal. This means that when we put a molecule into a solution where the pH matches its pKa, it can't make up its mind. Half the time it keeps its protons, and half the time it lets it go. If the pH is more acidic than the pKa, protons are more abundant, and the molecule favors the conjugate acid form. The further the pH drops below the pKa, the stronger this preference becomes. If the pH is more basic than the pKa, protons become more scarce, and the molecule favors the conjugate base form. The higher the pH rises, the stronger this preference becomes. So by controlling pH, I am controlling the ratio of conjugate acid to base form. The reason I control the pH of water in my experiments is because it determines the form my molecules take. The conjugate acid and conjugate base forms of a molecule can behave very differently, so I want to control how much of each is present. The same is true for our skin. The molecules in our skin have many sites where a proton could be added or removed. So before you go sticking your hand in, you might want to ask what the pH is. Because if sites that don't normally have a proton start picking up one, or if ones that should have a proton start losing them, it can really damage your skin. Maybe I should think twice before I sign up for that acid peel facial.